Hi, welcome back. In this lecture, I would like to talk about how to encode using quantum states non-integer data. So far, we've seen integer data. They might be also signed, and how to encode that in quantum states. In this lecture, I want to focus on non-integer data. It turns out that there are two common methods for representing real values in binary. The first one, that is the most used by traditional CPU, that is the floating point. And the second one that we're going to use in quantum computing is the so-called fixed point. A floating point representation is typically more flexible, is represented here in this diagram. A certain number of bits are dedicated for a so-called mantissa or significant, and a so-called exponent is taking a certain number of bits. So this floating point formulation is able to adapt to a range of values we need to express with a certain number of bits, and therefore is quite flexible. For simplicity in quantum computing, we use the fixed point formulation of a real value of data. So it's more attractive starting point because of this simplicity. A fixed point representation splits a register into sections. We have one section that encodes the integer part of a number. So we have here integer part, and these qubits are just dedicated to represent the integer part of our value. The integer part is expressed using a standard binary encoding with the higher qubits representing increasing power of 2. So if this is the lower qubit, so here we have to the 0, to the 1, and then increasing the qubit, higher weight qubits, we can represent higher increasing powers of 2. The second part, that is really the novelty about the fixed point representation, is to encode the fractional part using qubits. In the fractional part of the register, that is this one, qubits of decreasing weight represent increasing powers of 1/2. Right? So we're going to have 1/2, and then 1/4, and then 1/8, and so forth and so on. Fixed point are representing using the so-called Q notation. The notation of Q n dot m denotes an n bit register, so this is the total number of the qubits. And in this case, m is the number of bits or qubits that are being fractional. So this is part. The remaining n minus m is the number of qubits that we dedicated to represent the integer part. So in this case, n is the total part, m is the number of qubits we dedicated to express the fractional part, and n minus m is the number of qubits we dedicated to express the integer part. So here we see an example using a formulation q at 8.6 fixed point. This means that we are going to use 6 qubits to represent the fractional part, that is here, and then 8 minus 6 to represent the integer part. You see here a diagram of our number representing using the Q8.6 fixed point representation. When talking about the floating point representation, there are two important aspects that we need to take care of. The first one is the so-called range of the representation, and the second one is the accuracy of representation. So depending on the number of qubits that we dedicate either to range or to accuracy, we can improve in these two aspects. So for instance, we can represent this number here that we have on the slides by using a fixed point, by using different power of 2 for the integer part and the power of 1/2. Increasing the number of bits in the integer size of a fixed point register increases the range of representation that we can encode. So if we put more qubits on the integer representation, then we increase the range. On the other hand, increasing the number of fractional size increase the accuracy with which we can represent the fractional component of the number. So range is related to the integer part, and accuracy is related to the fractional part. We might want to decide the number of qubits either for the range and the accuracy, depending on the requirement of our application. This is the last slide of this lecture, and talk to you soon.